Lenz's law. Now it's time to explain the minus sign in Faraday's law. It's so important that it has its own law. The minus sign tells us that the direction of the induced EMF in a current loop is such that the resulting current produces a magnetic field that resists the change of flux through the loop. This is a direct result of the law of the conservation of energy. If the external field gets weaker, the induced current tries to replace the missing external field by generating a magnetic field to replace it. If the external field gets stronger, the induced current opposes the extra external field by generating a magnetic field opposing the change. Remember, only the magnetic field within the loop counts. Disregard the magnetic field outside. Here's our first example. Let's say that we have a loop of wire in a magnetic field, but then the magnetic field turns off. This changing magnetic field will induce an EMF in the loop that will generate a current in the counterclockwise direction. This induced current creates a field that is out of the page inside of the loop to oppose the decrease in the external field. The way I like to think of it is that the loop hates change. So if it had a field and then the field gets removed, it wants to replace it. So you use right hand rule to figure out what direction must the current be going in to replace the field that was there before. In this example, we start out with no magnetic field, but then the magnetic field is turned on. The current over here is going to try to cancel out this new magnetic field. So therefore, if it has a current going clockwise, if you use right hand rule, just pick one part here, do right hand rule, stick right hand grip rule, stick your thumb straight up, and then you see that inside the loop, the field is going to be going into the page. See how that's going to kind of cancel out this field that's coming out of the page? The changing magnetic field will induce an EMF in the loop that will generate a current in the clockwise direction. This current creates a field into the page to oppose the increase in the external field that is coming out of the page. It wants to cancel it out. Here we have a square loop of wire that is being brought into a magnetic field. The loop on the left is being pulled to the right by an external force. As it moves to the right, the magnetic flux inside the loop increases. See, more of these X's are now inside the loop, so the area is increasing. This induces a current in the loop that opposes the magnetic flux increase by creating a magnetic field that is opposite to this field. So the current is going to go in either clockwise or counterclockwise direction, whichever one will create a magnetic field that's coming out of the page. So since this external magnetic field is pointing into the page, the induced magnetic field will point out of the page to try to cancel it out. The right-hand grip rule indicates that the induced current must be flowing counterclockwise in order to generate a field that points out of the page within the loop. In this example, a bar magnet is being lowered towards a loop of wire. Below the bar magnet, the magnetic field lines point upwards. Remember, magnetic field lines point out of the North Pole all the way around back into the South Pole. So the magnetic field lines below this bar magnet are pointing straight upwards towards the South Pole. So you can see the magnetic field of the bar magnet is pointing upwards. As the magnet is lowered down towards the loop, more of those field lines are going to be going through the loop. The flux is increasing. Therefore, current will be induced that will generate a magnetic field pointing down in order to counteract the increasing magnetic field that is pointing up. Using the right-hand rule, we see the current must be flowing clockwise in order to create a magnetic field that is pointing down within the loop. There are many other situations that can be analyzed with Lenz's law by using the following instructions. The magnetic field due to the induced current points in the opposite direction to the external magnetic field if the external magnetic flux is increasing. It points in the original direction of the external magnetic field if it is decreasing, right? It wants to replace it if it's going away. The magnetic field is zero if the flux is not changing. It is zero because of Faraday's law. There is no induced EMF if the magnetic flux is constant. Remember that the external magnetic field and the magnetic field due to the induced current are different. Have you ever noticed that when you unplug an appliance that is running, there's a spark that jumps between the wall socket and the plug? This is explained by Lenz's law. As the plug is pulled out, the current decreases, collapsing its magnetic field. The change in magnetic field induces an EMF, which produces a current which is seen as a spark. This is one reason why you should always turn off appliances before you unplug them. The energy that was stored in the magnetic field transformed into the electrical energy of the spark. A loop is placed in a uniform magnetic field. Determine the direction of the induced current in the loop when the original field B increases. The original field is directed out of the page, and it's increasing in magnitude. The induced field will try to counteract that by creating its own magnetic field pointing into the page. All right, now we're going to have to apply the right-hand grip rule to see which direction the current must be going in order to create a magnetic field that is pointing into the page inside the loop. So if you pick a point on the loop and you just try one direction. Let's see, if the current's going clockwise, then you point your thumb down, you wrap your fingers, and you see that your fingers do point into the page inside the loop. So that is the correct direction of the current. A loop is placed in a uniform magnetic field. Determine the direction of the induced current in the loop when the original field B decreases. The first step is to figure out if the field that is created is going to be into or out of the page. In this case, because the external field is decreasing, the loop is going to try to make up the difference, right? The loop doesn't want the field to change. So if it starts going away, it'll start replacing it with the same direction field. Using the right-hand grip rule, you can see that the current must be going clockwise in order to create a field pointing in to the page inside the loop. A permanent magnet, a bar magnet, is pushed into a stationary ring that is suspended from a vertical string. What happens to the ring? How can we use Lenz's law to explain this experiment? Step 1. The magnetic field of the magnet is directed to the right. See, the lines point right out of the magnet towards the loop. As the magnet moves towards the loop, the amount of magnetic field lines that are going through the loop increases. The flux is increasing. Step 2. According to Lenz's law, the induced current will flow in order to counteract that field. It will create its own field going the other way. Therefore, using right-hand grip rule, you can determine that there must be current going counterclockwise. Step 3. The ring and the magnet will repel each other like two magnets that both have the north poles facing each other, right? Here we have a field pointing to the left. This is the same thing as if you had a bar magnet with the north side of the magnet up here. So those will repel each other. When the magnet passes the ring, it will face the ring with the south pole. So now the bar magnet has gone all the way through. And now, as it's moving away, the flux is decreasing. So the current will change in order to create a magnetic field that makes up the missing field. So this field now pointing to the right is decreasing. So the ring will create a field to the right that is increasing so that it can make up that difference. Therefore, the current will travel clockwise. And then the ring will be attracted to the bar magnet, because if you have these field lines pointing to the right, that's like the north side of the magnet. This is the south side of the magnet, so they will be attracted to each other. Currents are generated by a difference in electric potential, also known as voltage. Earlier in the course, Differences in electric potential were found by relating them to electric fields established by static charges. These electric fields are conservative fields. But the EMF and current described by Faraday's law, the direction specified by Lenz's law, is not the result of electric fields created by static charges. The electric field is created by a changing magnetic flux. This electric field is a non-conservative field. The electric field created by a static charge or generated by a battery is a conservative field. The force resulting from the field performs work on charges in moving them from place to place. The net work done in moving a charge depends only on the initial and final positions. It is a path-independent field, as it doesn't matter what path the charge takes to get from its initial to its final position. So let's say you have a location of voltage here and there. So this voltage is higher than this one. So we'll say voltage is 0 here, voltage is 10 there. And when we want to move a charge up the hill, work needs to be done by the electric field. But it doesn't matter if you go up the hill this way or if you take a path like that. All that matters is the initial voltage and the final voltage and the charge. Because of the path independence, the net work done by the force on a closed path where the initial and final position is the same is 0. At points in the path, there can be either positive or negative work, but they add to 0 for the complete path. Let's say you have an electric field here, and you take a charge, you move it from here this way, so you're doing work because it does not want to go this way. This is like pushing the ball up the hill. Then from here to here, no work is done because you're not changing voltage. From here to here, it's negative work, right? Because this ball is like rolling down the hill in the direction it wants to go. And then no work done when you move sideways along the hill. So they total up to 0 work done. On the other hand, the electric field created by a time-dependent or changing magnetic field is non-conservative. The path a charge takes due to this electric field makes a difference as to how much work is done on it. It is not path independent. The induced EMF performs work that is proportional to the change in magnetic flux, Faraday's law. When taken over a complete path of radius r, and the charge returns to its initial position, it has a non-zero value, unlike the conservative force produced by a charge or battery. So if the complete path is a circle, like the charge goes all the way around, then the distance that it has traveled is 2 pi r. All right, now let's look at the work done. So the work is force times displacement. Now, electric force is Q times E. In this case, because the magnet is moving at a constant velocity, there is a constant EMF happening, giving us a constant electric field. So we can replace ED with EMF. Remember VED from our uniform electric fields. So therefore, we have work equals Q EMF. EMF is change in flux over time. So you can see that the work done is going to be proportional to the change in flux. So as long as the magnetic flux is changing with time, the net work will not equal 0. The electric field lines for the conservative and non-conservative fields are different. For static charges, the field lines start on a positive charge and end on a negative charge, or they start on a positive charge and then end at infinity, like that. Electric field lines for a non-conservative field are closed lines, like this, encircling the time-dependent magnetic field.